Welcome. This lesson is on electric field strength and the characteristics of electric field lines, which is a subtopic of electric fields and charges in Unit 18, Electric Fields. By the end of this lesson, you should be able to define electric field strength as force per unit positive charge and use F equal to Q times E for the force on a charge in an electric field. Represent an electric field by means of field lines. Imagine a positive charge Q sitting in space and creating an electric field all around it. We want to know what the strength of the field is at point P. We can put another charge, a positive test charge small q at P, to measure the electric force F that acts on the test charge. The electric field strength at point P is defined as the force per unit charge experienced by the small positive test charge placed at that point. So, the electric field strength at point P can be written as E is equal to F over small q, and the SI unit is Newton per Coulomb. Electric field strength is a vector. It has the same direction as the force F. This is because the charge is a scalar that only scales the value of F up or down. Consequently, the electric force acting on the charge can be expressed as F equal to Q times E. The charge can be positive or negative. The electric force F will be in the same direction as the electric field if the charge is positive. The direction of the electric force will be opposite to the electric field if it is negative. Next, let's study the electric field patterns resulting from multiple charges and the characteristics of electric field lines. Consider a positive point charge interacting with a negative point charge. Electric field lines begin from the positive charge and end on the negative charge. The electric field strength at point P, due to the positive charge, is E1. And the electric field strength at point P, due to the negative charge, is E2. We draw a straight line that just touches the electric field line at point P. This line is called the tangent line, or simply the tangent to the electric field line at point P. So, the direction of the resultant electric field strength at point P is along the tangent to the electric field line at point P. Electric field lines never intersect because we may have two directions of the electric field at the point of intersection, which is not possible since the set of field lines represents the resultant field of all the contributing charges. The closer the spacing of the electric field lines, the stronger the electric field strength. For example, consider the electric field around two positive or two negative point charges. There are 2 points, point A and point B, in the electric field. The spacing between the electric field lines at point B is closer than the field at point A. Hence, the electric field strength at point B is stronger than the field at point A. A positive point charge is placed near an oppositely charged flat plate. The electric field lines meet the surface of the plate at right angles to it. This is because charges on a conductor will always move to the surface to be as far away from each other as possible. If the field lines are not at 90 degrees, these surface charges will interact with the electric field that is at the surface. The horizontal component of the electric field Ex will cause a force component to the right along the surface. This force component Fx will then move the charges along the surface until the charges settle into a final distribution that results in the field lines becoming perpendicular to the surface. Hence, the electric field lines always leave or end on a conducting surface at right angles. Let's try some examples. Please pause the video to try the question. In this question, an electron is placed in a uniform electric field. The electron will experience an electric force Fe. Since the electric field is uniform, the electric field strength is the same anywhere in the field, so the electric force is constant, which causes a constant acceleration. We recall that, when a charge is in an electric field, the electric force is the product of the charge and the electric field strength. So, the electric force Fe equal to Q times E. Because the weight of the electron is much smaller than the electric force, the weight is negligible in this question. Then the electric force can be considered equal to the net force. By Newton's second law, the net force is equal to mass times acceleration. Combine the two equations, we get the equation m times a equal to q times e. Rearrange the equation to get the acceleration a equal to q times e over m. The amount of charge carried by an electron is 1.6 times 10 to the power of negative 19 coulomb. The electric field strength is 1,500 Newton per coulomb. The mass of the electron is 9.1 times 10 to the power of negative 31 kilograms. Substitute the values into the equation to calculate the value of the acceleration, which is 2.6 times 10 to the power of 14 meters per second square. Hence, option D is correct. We have come to the end of this lesson.